Okay, you can give your attendances. I've started recording. All right. So as you can see, we will continue with classical field theory. So not yesterday, in the previous class, we made a point that uh, for mechanics of continuous media, we can define something called a Lagrangian density, from which we can find out the equation of motion for the field. Okay, so this is so the field is the thing that carries information about the continuous medium of the system, and mm, from the field equation we should be able to uh, figure out the properties of the system or how the continuous medium should behave. And we suggested that in terms of that Lagrangian density, we can define the action now in this way. And a minimization principle, like you have to minimize this action, or the principle of least action. So what you do is that you vary your fields uh, about the something called the classical field. So you vary, so the variational principle. So if you want to minimize S, suppose S will be minimum for eta equals to eta 0 xt. Okay, so S will be minimum or extremum actually. So minimum underscore for say eta equals eta 0 xt. So then what you do is that you define a general eta. So a general eta xt with parameter alpha, you define it as a perturbation about that correct field, the minimum field. So this eta 0 xt is your correct field, which we will call the classical field, which minimizes my action, and plus some alpha times some xi xt, in the same way that we did the minimization of action in our discrete point mechanics. Okay, so in the same way we can proceed, and now I can perhaps demand that this ds d alpha should be equals to 0, and from that I can find out what kind of equation this eta should satisfy. So this should give me the equation of motion for eta xt. So if you do this exercise, this exercise has been done in many of the textbooks. So you may want to do this exercise, and you will find that the field equation looks like this. So the field equation, so the equation of motion for eta xt, the equation of motion for eta xt. So that will, the final result will be d dt of del L over del of d eta dt, which is basically eta dot, okay, plus d dx, so del of del L del of d eta dx, okay, minus del L del eta equals to 0. So this is my equation of motion in terms of eta xt. Okay. Now this can be written in a compact notation, in a more compact notation. So as I discussed in the earlier class, here the time derivative and the space derivative are treated in parallel, treated very similarly here. Okay. So what you can write it in a more compactified notation is by introducing those relativistic notations. So the relativistic notation would be that you use your x mu is equivalent to say x0 and x1. Since I have only one space coordinate, I call it x1, let's say, and that is equivalent to say t and x. And then you can also write del mu equals uh, del x0 and del x1, so which would be equivalent to del t and del x. Okay, so if you remember this, then you should find that the first term here, so now let me rewrite this thing. So the first term is basically del 0. So the outside, this is del 0, this is d dt, this basically del x0, I call it del 0, and this is my del 1, let's say. Okay, so the exterior derivative you interpret as a total derivative. Just I am writing in this notation so that I can use this notation here. Okay, so then you have del L, del of, notice this is del 0 eta, okay, because this is del eta del t. So d eta dt and del eta del t is the same thing because now x and t are independent. So when you are taking the derivative of the fields with respect to the space-time coordinates, it doesn't matter whether you take partial derivative or total derivative, they both mean the same thing because the t and x are independent coordinates now. Okay. So and the next one would be del 1 del L del of del 1 eta, okay, minus del L del eta, that should be equals to 0. So employing the summation convention, I can, so this is basically 0 0 then 1 1. So employing the summation convention, I can compactify this thing as like del mu del L del of del mu eta, okay, minus del L del eta equals to 0. Just keep in mind is that the exterior derivative is the total derivative. So this is the total derivative. This is basically d dx mu, what I mean by that. Okay. So it will be useful if L explicitly depends on the x and t, which is not very often, but if it does, then remember to interpret this as d dx mu. Okay. So this is a compact notation for the equation of motion for eta. Okay. Now you might have you have only one field, but in general you will have uh, many other fields. Okay. So suppose you have n number of fields. Okay. So suppose you have n number of fields. So those fields are say eta 1 xt, then eta 2 xt, and so on, support up to the eta n xt. Okay, so you have n number of fields, and for the, let's say for the eighth field, okay, so the eighth field is denoted by say eta a xt, and a can take any values from 1 to n. So a can be 1 to n. Okay, then for each of these fields you will have equation of motion like this. Okay, so each of these eta fields you will have equation of motion like this, and usually you have n number of equations of motion. Okay. I will at the end I will talk about an example, but for now you can perhaps understand that for each of those fields, this equation of motion will be satisfied separately. So for eta a xt, the del mu, quite obvious that you replace this eta by eta a. So this is del mu eta a minus del L del eta A, that is equals to 0. Okay. So you notice that so there are n such equations. So there are n such equations. Okay. So this is for eta A. And now that I have come to learn this compactified notation, now I can assume that I can write my Lagrangian in a very compact way. That my Lagrangian depends on my fields, my field derivatives, so del mu eta A, and then the coordinates x mu. So this is the my Lagrangian. So when I talk about Lagrangian in the context of classical field theory, I always imply Lagrangian density. So my Lagrangian density basically depends on these three quantities: field derivatives, and the space-time coordinates itself. Okay. Now, similar to again similar to discrete mechanics, we can find certain conservation laws in the continuous case also. To give you a glimpse of what kind of conservation laws we talk about, and what general ideas can we get from those conservation laws, let us look at the total time derivative of L. Okay, so let me start something called the conservation say conservation theorems. So again, basically I start with this Lagrangian. So this Lagrangian is in general a function of eta A, the derivatives of eta A and x mu themselves. Okay, and that implies, so if I take the total time derivative of this Lagrangian, so this dl dx mu, let's say, and that should be given by chain rule of derivative again. So del L del eta A and then del mu eta A. Okay, so this is the first term. Okay, plus del L del of del mu eta A. Okay, or rather I can put it, I should let me write this as del nu eta A, so not to confuse this mu with this nu. So this is a different index here. So del of del nu eta A, and then I have del mu del nu eta A. Okay, and then you get del mu L, which is basically del L del x mu. Okay, so these are the three terms you get. This is the chain rule of derivative, and that's what it gives you. Now, by the way, here summation convention has been employed. So basically, there is a sum. The repeater index are summed over. So this nu is summed over, and also this a and a is summed over. Here also a and a is summed over. So you are basically summing over all the fields here. Okay. So let me write it explicitly. So summation convention employed. All right. Okay. So again, let us then rearrange the terms here. So dl dx mu, and so first of all this term. Okay. So this term here, I can use the equation of motion to replace this term. So d del L del eta A is basically del mu del L del eta UA. Okay. So that del mu, remember to interpret it as a total derivative, as I told you. So uh, that I interpret as, so I can write this thing as d dx nu of del L del of uh, del of del nu eta A. Okay. So basically from here, basically I am replacing the dummy index mu by nu. That's the thing I am using here. And then del mu eta A plus, now you have to be careful. So this is del L del of del nu eta A, and then again I interchange this mu and nu, like reverse the order, it doesn't matter. The del nu of del mu eta I can write plus del L del x mu. Okay. Now look at the first two terms on the right hand side. So this term and this term. So this is basically, so if you write them together, let me first write them together and then it will be much easier to see. So this is t dx nu of del L del of del nu eta A times del mu eta A. So basically this is the product rule of derivative. So the first term is the derivative of this term times the second function unchanged, and the second term is that the derivative of this term and the first function unchanged. Okay, and that then it is plus del L del x mu. Okay, now I can rearrange this term, so I can um, I can take this one on the left hand side and take this one on the right hand side to write down. So I will write minus del L del x mu equals d dx nu del L del of del nu eta A times del mu eta A, this thing, minus dl dx mu. All right. So I'm going to write the second term in a bit more fancy way. So this dl dx mu is basically, let's say, dl dx nu times delta. This is a covariant index, so I have contravariant index, so delta nu mu. Okay, so this nu and nu contracted gives me just mu, so I can write it at dl dx mu minus delta mu nu. Okay, delta nu mu. All right, so if I take d dx nu common, so this is d dx nu times del L del of del nu eta A times del mu eta A minus L times delta nu mu. Okay. So I am going to call the term inside the square bracket. This is a second rank tensor. I am going to call it a T nu mu. Okay. So my equation becomes then this is d x nu of T nu mu equals minus del L del x mu. Okay. Now, again, if L does not explicitly depend on my space-time coordinates, so if L does not depend on x mu, then the right-hand side is 0. So this is 0 if L doesn't explicitly depend on x mu. So then you have a 4 divergence kind of thing. So you have the equation of continuity like thing. So T nu mu equals 0. So this is a conservation equation of T nu mu. Okay. So that means that this T mu nu, the T nu mu is conserved. Okay. And so what is the meaning of this T nu mu? This T nu mu is sometimes called the stress energy tensor. So this is my trace energy tensor. And the T nu mu would be given by this thing. Okay, just light massage. This gives you the definition of your T nu mu in a certain way. Now, why do we call it the stress energy tensor? I mean, to find out the energy component of T nu mu is quite easy actually. So let me so just for fun, let us calculate the 0 component of this T nu mu. Okay, so let us calculate T00. So this T00 is just by replacing you replace nu by 0 and mu by 0 also, and remember delta 00 would be 1. Okay, so it has the same structure. So this delta 00 should be 1, and then you have everything 0 here. So then T00 looks like del L del of del 0 eta A times again del 0 eta A minus L. Okay, so you compare with this. You compare with this. So this is del L del 0 eta. That is it. And again, del 0 eta is just eta dot, right? So this is del L del of eta A dot, and this del 0 eta is again your eta A dot minus L, right? So this is my T00. Now, again, if you are being observant, you can probably see where this is going. So now again, draw your intuitions from discrete mechanics. So from discrete mechanics, what you defined is that you defined a generalized momentum pk to be your del L del qk dot. I told you that the role of qk is now taken by eta A. Okay, so when you're trying to connect between this classical field theory and the discrete mechanics, so the qk, basically the sense of coordinate is carried out by the field itself. Okay, So this is my field now, eta A. So in a similar way, I would mm, I would be tempted to define something called a momentum density, which I denote by pi a, which is given by del of Lagrangian density times del of del eta a dot. Okay, so this would be some sort of a momentum density. Okay, because it comes from a Lagrangian density, it becomes my momentum density. So then this t00 thing, okay, this becomes pi a times eta a dot minus L. Remember, summation convention have been applied here. So this sum over A is there. So again, you compare this with the definition of the Hamiltonian. So Hamiltonian, how did you define is summation over Pk Qk dot minus capital L. So this again looks similar to that. This is the momentum density times the coordinate derivative summed over minus the Lagrangian density. So this is again a density which I will define to be my Hamiltonian density, which is H. Okay. So I find out that the 0, 0 component of the stress energy tensor, whatever that is, that gives me something like a Hamiltonian density. Okay. So this and since I know that there is a connection with the Hamiltonian and total energy, so there is a connection between Hamiltonian and total energy. So this Hamiltonian density can somehow be connected to the total energy density. Okay, so that's why we say that the 0, 0 component of the stress energy tensor is basically the energy density. Okay, so so T00 is basically the total energy density. Okay, in this sense of I mean drawing parallel mm, from our knowledge of discrete mechanics. Now, one small comment I want to make is that this indices, one upstairs and one downstairs, okay, was intentional. So if you want to, for example, whether T mu nu is symmetric or T mu nu is antisymmetric, to judge that, you need to remember that this mu and nu should be either both covariant index or both contravariant index. So for that, you should construct, mm, mm, say, T, let's say nu sigma, which is equivalent to T nu mu times the metric tensor, which is the G mu sigma. Okay, so you multiply T mu nu by G mu sigma, and you get T nu sigma, and that is just equals del L del del nu eta A times del sigma eta A minus L times G nu sigma. You can easily find it out from the definition of T nu mu. So from the way I have written this T nu sigma, it does not appear, I mean, the last part is symmetric, of course, but this part does not look very symmetric in nu and sigma. But the thing is that since the four divergence of T mu nu equals 0, okay, since using this equation, I can add to this a function whose four divergence also 0, because that will not change this equation, and I can then symmetrize this T nu sigma. So I will not go into the detail of this thing, but just keep in mind that this rank 2 tensor can always be symmetrized. Okay, so it can always be chosen to be symmetric. So and can be chosen to be symmetric tensor. Okay, so this is the thing, and we usually choose this T mu nu to be a symmetric tensor. All right. So these are some of the comments you for regarding the stress energy tensor, and for different Lagrangian densities, it's a good exercise to calculate the components of T mu nu. So Ti0, T0, it's an interesting exercise. I don't have time to cover all of those, but since you know now how to calculate the components of T, and perhaps you can now do it yourself. That how to calculate the other components of this T. Now I will rush to something called the what is the version of Noether's theorem in continuum mechanics. So how does Noether's theorem look like? So Noether's theorem in classical field theory, let's say continuum mechanics. Okay, so Noether theorem is basically deals with symmetry. Okay. Now, when we talked about symmetries in the case of discrete particle mechanics, then we talked about symmetries of the physical coordinates, like symmetries that you could visualize somehow. It was either translation or rotation, because those qk and pk to some degree were in our hand. Okay, like you can visualize. Sometimes it can be interpreted as actual coordinates, maybe Cartesian coordinates, sometimes polar coordinates. But here, the role of the coordinates is played by the fields. And fields, by definition, are an abstract concept. And we would be talking about symmetries of the field. So we would be talking about symmetries in a more abstract sense. Okay? Um, so we will be talking about symmetries. Sorry. Symmetries of fields. So that gives more abstract, more abstract version of symmetry. So essentially, we are extracting our main main inspiration from discrete mechanics, and from the symmetries that we could visualize, we could touch, and we could feel, we are elevating our understanding of symmetry, or we are extending those understanding of symmetry into a more abstract framework. And believe it or not, it is extremely powerful tool. I mean, I will show you just one example, and you will realize the power it contains here. And that would be the final thing of that of my today's lecture, and that would be the end of my classical mechanics part. I would be leaving you with that, and you will think what you can do with that. Okay. So it would be finished on open end. Okay. So let me start by explaining what I mean here. Okay. So again, suppose you have a Lagrangian that does not explicitly depend on the space-time coordinates. In other words, so you have a Lagrangian that depends on the fields and the field derivatives. Okay, and nothing else. Okay. Now, first of all, let us say that these fields are being transformed infinitesimally. So first, let's say fields are being transformed infinite simile. What I mean by this is that suppose the eighth field, which is given by eta a x mu, it is transformed to eta a x mu plus epsilon times say alpha a x mu. Okay. So the eighth field is transformed by alpha a. Okay. So the eighth field is changed from its original to the first order alpha a. Okay. So as a result, if you change the fields by this amount, in general, your Lagrangian will also be changed. Okay. So the Lagrangian, so because of this change, the Lagrangian changes as, let me write down this, then this L transforms into L plus epsilon times dl day epsilon, just Taylor series. So this is up to first order. So rather, up to first order means plus order epsilon square. So up to first order, Lagrangian change, first order changes this. Now, how to calculate this dl d epsilon? In the same way as we did in our case of discrete mechanics. So this dl d epsilon is equals to del L del eta A times del eta A del epsilon plus del L del of del mu eta A and del of del mu eta A or del epsilon. Okay. So first of all, from here, you can easily recognize that if eta changes into this, then the change is basically del eta del epsilon is basically alpha A. So that implies del eta del epsilon is basically alpha A. And similarly, if you just put del mu eta here, so then del of del mu eta del epsilon will be just del mu alpha A, nothing else. So if we try to write down the next line here, so this piece is just alpha A plus this piece is just del mu alpha A. Okay, I will not do anything with this part, so I will just keep it as del of del mu eta A. But again, with this part, I will use my equation of motion. So this comes from here. So if I use the equation of motion, so this is del mu of del L del of del mu eta A. Okay, so it comes from an equation of motion. Now, again, you look at these two pieces together, and it looks like, so this is del mu of del L del of del mu eta A times alpha A. Okay, that's it. So that if you now distribute the derivative operator, so it's again the product rule of derivatives. So derivative of the first and the second function unchanged, and then derivative the first function unchanged and the derivative of the second function. So you have this thing. Okay, and I will write this thing in a more fancy way. So I will write it as del mu j mu, where j mu is basically the term inside the square bracket. So j mu is del L over del of del mu eta A times alpha A. Okay. Now, now comes the familiar thing. Now, if this change in eta is a symmetry operation, if this is this thing in the red box, if this is a symmetry operation, so suppose I say this is a symmetry operation. So if you make this change to your fields, okay, if you make this change to these fields by this, and if that is a symmetry operation, then that means because of this change of in fields, my Lagrangian does not change, at least up to the first order. That means this dl d epsilon should be 0. So again, this dl d epsilon vanishes if the change in that because of that change in the field, my d epsilon goes to 0. Okay. So if so basically if that is a symmetry operation and that is dl d epsilon equals to 0, then that implies del mu j mu equals 0. So again, this is a conservation equation. This is just the conservation equation. Like, so if you expand this thing, so it is just dj dt dj0 dt plus del dot j equals 0. So that means dj0 dt equals minus del dot j, I guess. Okay. So that is the thing that you have here. And if this holds, then you know that if you integrate the whole thing over the 3 volume, so you write it as like d dt of integration j0 dv, okay, equals minus of del dot j dv in integration. So the second term, basically you say that you change it to a surface integral. So you say this is a closed surface and the surface is taken to at infinity is j dot ds. Sorry, missed a minus sign. And if then you say that if my uh, at my surfaces, if I take the surface at infinity and all my currents vanishes at infinity at the boundaries, and the right hand side is 0. Okay, so this surface integral basically vanishes. Then what you have is basically d dt of this thing that you call the total charge q was 0. So usually when you write the 4 current vector, perhaps I told you before also, in the 4 current vector, so j0 is written as rho, sorry, j mu is written as rho and j. Okay, so the 0th component of a current is usually interpreted as a charge density, some sort of a charge density, precisely because if the current satisfies my equation of continuity, then I know that the time that the time derivative of the total integral of the 0th component of the current uh, is 0. And if I want to interpret that to be a total charge, then J0 should better be J0 should better be interpreted as a charge density. So, so I noticed that if there is a symmetry operation, there is a symmetry that can be found here. And so under this infinitesimal symmetry, if my Lagrangian does not change, then there is a conserved charge in the theory. Okay, and that conserved charge is called the Noether's charge. Okay, so and by the way, this infinitesimal transformation are properties of continuous symmetry. So that means by definition, my symmetry that I'll be talking about are continuous symmetries, and by definition, then if there is a symmetry of continuous nature, then I can find something that is conserved, and I can find an analog of a charge, a general analog of a charge that is conserved, and I will call this thing to be my Noether's charge. Okay, so and similarly, this current that I defined here, this is called the Noether's current. Okay. Okay. So this is very general. Remember, it doesn't. I have not here even told you what are my eta A. Okay. So this is a general theoretical framework that I am developing, and I am saying that if for a theory I can somehow guess a Lagrangian density that is of this form. So I want to construct a theory, and theory is described by some abstract field which I called, say, eta A. Okay, there may be many fields many independent fields which I will call like eta 1, eta 2, label with that. So I'm constructing a theory with certain fields inside, and my only point is that I can somehow guess the Lagrangian. Okay, I am not answering the question yet. How can I guess the Lagrangian? That is a whole different discussion altogether. But if I can somehow write down a Lagrangian involving fields to describe a certain system, and if that Lagrangian possesses certain symmetries in terms of those fields, so if you change those fields, my Lagrangian do not change, then in that general framework, you can define a current, okay, and that current will be conserved in the same way, like equation of continuity, and that you can define something called a Noether's charge, and that will not change with time. That means the total time derivative of that charge to be 0. Okay. But so far, these are so abstract. This doesn't mean anything to you, and I totally understand that. Okay? That these are all new, and you are perhaps worried, why do we even bother about this? I mean, we started up nicely by trying to develop the wave equation in a one-dimensional dot, but now things are just going out of hand. Okay, and you do not seem to get a sense of where things are going. Okay. So that's why I decided to include as a final example um, the example of Schrodinger field. Okay, let's see. So let me give you an example of Schrodinger field. By the way, do you remember that for Schrodinger equation, which is I guess minus a square by twice m del square psi equals I h cross del psi del t. For this Schrodinger equation, do you know that the total probability, if you define p to be psi star psi dq bar or dv, I was writing dv, then this probability doesn't change with time, so dp dt equals 0. So did you prove that anytime in your quantum mechanics courses, maybe in bachelor's, maybe in master's? Yeah, you did that, right? Good. Sorry, I forgot the potential term, the Vc. All right. Now we will connect these things with the formalism that we developed right now. So in the last class, I gave you a hint that if you start with this Lagrangian, so suppose a Lagrangian was h squared over twice m grad psi plus h cross over twice I psi star psi dot minus psi psi dot star plus v psi star psi. Okay. So first of all, you notice that suppose this is the Lagrangian. This Lagrangian is given somehow. I have not discussed how you get this Lagrangian, but somehow you got this Lagrangian, let's say. And this psi is a complex field here. So a complex field has 2 degrees of freedom, okay, because the real and the imaginary part. Or you can take the field and its complex conjugate as your 2 different degrees of freedom. So I have basically 2 independent fields here. So if I, in my notation, so eta 1 xt should be equivalent to psi xt, and eta 2 xt would be equivalent to psi star xt. So these are my 2 field, my 2 independent fields here. Okay. Now you can check, and I will leave it as a homework to check for yourself. So you can check the equation of motion corresponding to eta 2, that is psi star. If you calculate the equation of motion, you will precisely get the Schrodinger equation for psi. You will get minus h square over twice m rather del 2 psi plus v psi equals I h cross del psi del t. Just you can check that. And if you try to find out the equation of motion corresponding to eta 1, you will get the Schrodinger equation, the complex conjugate of Schrodinger equation. All right. Now, this is not the most interesting part. So I do not even want to know this equation of motion. Okay. Suppose I did not do this part. Okay. So suppose I did not do this part. Okay. I didn't know about the equation of motion at all. Okay. I just look at this Lagrangian here. I see that this Lagrangian contains a symmetry. Okay. So this symmetry is this. So I notice that the Lagrangian has a symmetry. Okay. Now the symmetry, if you notice, is that if you change psi to psi prime xt, which is just a phase, so e to the power I epsilon psi xt. So obviously the star, the complex conjugate of psi will be changed to e to the power minus I epsilon psi star xt. So you notice if you replace psi with psi prime here and psi star with psi prime star here, then in each and every term e to the power plus epsilon and e to the power minus epsilon will cancel out, and you will have the same Lagrangian. Okay, so this Lagrangian has a symmetry. It's a very simple symmetry. It's a phase symmetry. Okay, and so this is basically a common knowledge from your quantum mechanics, that introducing a phase, an overall phase to the wave function doesn't change anything. So somehow that information is encoded in the Lagrangian, and that information, so when I tried to write down this Lagrangian, that information was there. Okay, so this is the symmetry of the Lagrangian. Now to get an idea of the how to apply my Noether's theorem here, I need to look at the infinitesimal versions of this symmetry. So let me look at the infinitesimal version. That means epsilon tends to 0, so that you keep only first order in epsilon. So what you have here is that psi xt goes to psi xt plus I epsilon psi xt, because remember this e to the power I epsilon is just 1 plus I epsilon in the limit epsilon tends to 0. So psi xt just changes to psi xt plus I epsilon psi xt, and psi star xt equals psi star xt minus I epsilon psi star xt. Okay. So the notations that I have developed in using eta 1 and eta 2, so it is uh, better to think in terms of eta 1. So here you see that eta 1 changes to eta 1 uh, plus I told you that it should change to some epsilon times alpha 1. So if you compare this, then this alpha 1 turns out to be I times psi. Okay, so this is the change in eta 1. Okay, and psi star is my eta 2. So eta 2 then goes to, sorry, eta 2 minus if I write it as plus epsilon times alpha 2, then this alpha 2 is basically minus I psi star. So I have identified my alpha 1 and alpha 2, and I know my Lagrangian. That's all I need to calculate my Noether's current, all of my Noether's current. Okay, to calculate the J mu, and that's all I need. Okay, what is my J mu? So this is my J mu. Okay, just to be illustrative, I will focus on J0, and I will leave it as a homework to figure out what are your J vector. So if I now try to calculate, say, J0, so J0 will be what? So this J0 will be del L del of del 0 eta 1 alpha 1 plus del L del of del 0 eta 2 alpha 2. Again, go back to this definition. So here A is repeated, so there is a sum over A. Okay, so I have chosen mu equals 0, so that's why I have put um, J0 there, and that's it. Okay, that is what I have. Okay, so let us calculate then. So this is del L this is del 0 eta 1. That means eta 1 is psi, remember. So this is del L del psi dot times alpha 1, and alpha 1 I will write it in a different color. This is I times psi. Again, plus this is del L del of psi star dot, and alpha 2 is minus I psi star. That's it. Now I have to find this derivative. What is del L del psi dot? So this del L del psi dot comes from this term, is just h cross over y psi times psi star, right? So if you take del L del psi dot, this is h cross over y psi times psi star. So this is cross over y psi times psi star times I psi plus del L del psi star dot. So this psi star dot here. So del L del psi star dot is just minus, so this minus sign is here, minus h cross over y psi times psi. So this is minus cross over y psi times psi minus I psi star. Okay. So notice that both of them denote the same thing. You cancel out I and I here. Here you also cancel out I and I. And what you are left with is h cross times psi star psi. So both of them are h cross by psi star psi. So notice what was my Noether's charge. So Noether's charge that is conserved is Q is J0 dV. So the Noether's charge in here, the thing that is conserved, this q that is conserved here is just integration of j0 dv, okay, or integration, let's say h cross is psi star psi dv. So that is your total probability. So notice the power here. So now I am saying that my total probability is conserved. Okay. So in the case of your usual quantum mechanics, the non-relativistic quantum mechanics, uh, by the way, this Lagrangian is non-relativistic, you can say, because the time derivative and the space derivative have been treated differently. Anyway, so I'm not getting into that. So in your non-relativistic quantum mechanics course, you learned a total probability to be conserved. That the total probability does not change with time, and the reason for that you didn't know. It just comes out to be that way. Yeah, it comes out to be that way by design. I mean, if I ask you why does your total probability conserved in your quantum mechanics, then you say, oh, from Schrodinger equation we can prove this. That's it. But now you have a deeper understanding of why your probability is being conserved, because the thing that you call Schrodinger equation can more generally thought to be comes out from something called the Schrodinger Lagrangian that involves these abstract fields. And the Lagrangian is constructed such that this Lagrangian has an inherent symmetry. Okay. And because of that symmetry, the Noether's charge, which is a general class of conserved quantities, and the total probability in your non-relativistic quantum mechanics is just a special case of a very general quantity that is called the Noether's charge. Okay. So the trend that I am trying to set here is that whenever you see that there is some conserved quantity, it is not just because of mere accident. It's not just special to that particular problem. There might be a general reason, there might be a general principle from which that conservation laws come from. Okay, and that's why uh, after let's say this non-relativistic quantum mechanics and let's say 1900s and early 1900s, we moved on from trying to decode the physical laws for each individual system. Rather, we start by guessing the Lagrangian. We want to describe any system, then we start by guessing the Lagrangian, and we notice if the Lagrangian possesses any symmetry. If it does, and usually it does possess many symmetries, then there would be certain conserved quantities. Okay. And we basically look at those. So this is the power that classical field theory, or thinking in terms of this Lagrangian and field equation, this is the power it gives you. It readily makes you aware of, like, for example, in this calculation, from arriving at the conclusion that this thing is conserved, I never talked about Schrodinger equation. I only mm, talked about this Lagrangian. Just from this Lagrangian, this inference can be obtained. Okay, you twist this Lagrangian, that thing will not be conserved anymore, or maybe something else will be conserved. Okay, so this Lagrangian formalism, or this classical field theory formalism, gives you a very general setup to describe your physical systems. So in terms of now you know that quantum mechanics can be described using the languages of a field theory. In this case, it's a classical field theory. So still, it can be described. The quantum mechanics can be described using a classical field theory. I have already told you that electrodynamics can uh, also be dealt with classical field theory. So now you see the unifying power of this field theories thing. So, for example, to you so far it was like quantum mechanics was a different topic. Electrodynamics was a different topic. And I am just saying those are basically the same. Those are two different aspects of two different field theories, starting from two different Lagrangians. That's it. Okay. So once you understand what is a field theory and what kind of information does your field contain, then you have a unifying picture of nature that otherwise is very difficult to obtain. I mean, you put all your physics information in the same thread. So I will leave it at this point, and I will. By the way, just calculate the space component of this J for this Schrodinger thing, and just uh, check that this gives you the usual probability current density for your quantum mechanics. Okay. So that probability current density that you calculate in quantum mechanics, which gives you this equation of continuity, is basically the example of, again, the space component of Noether's current. So I think I will close this lecture here. And there are many interesting things that I could not discuss, like how the concept of Poisson bracket can be applied here, which is not so straightforward in here. And the Hamiltonian formalism, it has some mm, we have to take special care when you try to do Hamiltonian formalism in this classical field theory picture. But hopefully still you have uh, enough overall idea to grasp the attractive features of this, some of the attractive features at least of this classical field theory. I hope it was like not too technical or like not too boring, let's say. Okay, so I will just stop here, and I will pause for questions now.
Sir,
Yes.
how can I know that this T nu mu is the stress energy tensor? Why is it named so?
Oh, the energy component I already showed, because the T00 is the energy, is your Hamiltonian. Okay. And
Yes.
if you check if you calculate the this block, the TII block. So what did I write there? I didn't calculate it, but in many textbook it has been calculated, so you can check that. So this is a 4 by 4 tensor, right? In the usual sense, in 3 space and 1 time, like. So
Hmm.
this 0 0 component is your energy. If you calculate uh, this 3 cross 3 block here, like Tij part, for the example I showed you for one-dimensional elastic rod, for example, actually. So for one-dimensional elastic rod, it is basically just this part. It's just the two element, and that will come out to be a stress. Okay. And for many spatial dimensions, like for 3 spatial dimensions, this 3 cross 3 block turns out to be a trace tensor. If you calculate it explicitly from that field Lagrangian for a continuous metal rod, in that case it will not be a rod; it would be a rectangular bar. So it's a three-dimensional version of that thing. And if you calculate that, it will come out to be the stress tensor, the sigma xx, sigma xy. I don't know if you have seen it in your elasticity course.
Okay, sir. And one more question is, here you say that zero zero is the Hamiltonian density in analogy to the discrete mechanics.
Yeah.
But sir, these Hamiltonian dense or in the discrete mechanics, this Hamiltonian is not always the total energy.
Here also it is not, but we want to give it a name, so we just think it about when we try to give it a name, we just interpret it as an energy, as the field energy.
Oh, it means that it can be different from energy, what we actually mean of that.
Yes, actually, this uh, it depends on what you understand by energy. It is not it is not your usual kinetic and potential energy. If you calculate, for example, in electrodynamics, you know what is the field energy density? Have you ever seen expressions like this? Half epsilon 0 E square. This is
Yes,
my field energy density for electric field, and for magnetic field we have a similar expression, half mu 0 B square, or B square by mu 0 perhaps. I forgot what is. Yeah. So for an electromagnetic field, the Lagrangian of electromagnetic field is given by -1/4 f mu nu f mu nu. If you calculate this thing, it comes out to be this. Okay.
Okay.
So that's why this is your field energy density. So this is the energy carried by field. For electrodynamics, I can give you this example, but for other fields, it has a more abstract meaning. So in the same way that these fields carry certain energy, in the same way you can also assign, let's say, if you calculate T00 for this, Schrodinger field also carries some energy. Okay, so in that sense, this is my field energy.
Okay, sir.
Okay.
Sir, why you took that J dot ds closed loop integral as 0? So can you please repeat that?
Yes, if your currents vanishes at the boundary, so no current element, like no source element, extends up to infinity. Like your current is localized. That's what it means. That's
Okay.
the surface integrals. You are integrating on the surface. So if the surface is at infinity and none of your sources are present at infinity, then that is 0. Is the standard equation of continuity thing. I mean, you open up any textbook, and you check the part where it discusses equation of continuity. And in fact, when you try to prove this dp dt equals 0 for quantum mechanics, you also use this fact. You say that the psi star psi falls off very quickly, so that the probability current density at infinity is 0. You use this actually.
Okay, sir.
Okay.
Sir,
So,
give some books of classical field theorems from where.
so this part I was taking from Goldstein, Herbert Goldstein. I think chapter 12 or 13, depending on which edition you were looking at. It's a good book. The book by Landau and Lipschitz is a very good one for classical field theory. Okay. See, my objective for classical field theory was not to stop here where I stopped. My objective was how can you. So, for example, when I talked about Poisson bracket in discrete particle mechanics, I could connect it with your quantum mechanics class, like just by extending those Poisson brackets and interpreting them as commutators of operators. And those operators live in a space called Hilbert space. And then you assign meaning to your psi and those vectors, and you get quantum mechanics. That's it. So from here, if you want to quantize the version of this classical field theory, like what is the equivalent of Poisson bracket here that I had to define, that I did not have time to define here. And then you will interpret certain things as operator, and you will assign meaning, and then what you get is quantum field theory. I mean, it's quite a smooth transition from here to here, and it will give you an essence of quantum field theory. But anyway, hopefully you will learn that in your third semester, I guess, if someone is interested in doing this. So you are going to learn that. So that was my motivation, but I couldn't follow it. But in general, any book of quantum field theory also starts with a discussion of classical field theory. So if you take out any book on quantum field theory, just stick to the first chapter, then you will get these things.
Okay, sir.
Sir, how would symmetries look in the spatial part? Like we took only mu is equal to 0 thing.
In nu
For,
equals 0. Yes, because
and
so
other,
you are talking about J0 now, right?
yes, sir. I'm asking about for the case of like four-dimensional curve space-time, 1 to 3 parts. How would the symmetries look like?
No. The conservation rule is this. The conservation rule is already symmetric in 4 dimension. So the conservation rule is del mu J mu equals 0. That's the conservation rule. All the 4 components are here. When you try to interpret this in a traditional sense, then you say that the time derivative with the 0th component is 0. So this is the conservation rule actually. Del mu J mu equals to 0 is your conservation theorem. Okay. Since you are familiar with conservation in terms of time, that's why you take out the 0th component, because the 0th component contains a time derivative. So del 0 is the time derivative. Do you understand what I'm trying to say here? In general, the conservation theorem is del mu J mu equals 0. Hello? Who asked this question? Have you seen an equation of this form? So this is your del mu J mu equals 0. So the same way you interpret this, this is the equation, the conservation equation, the equation of continuity. From this, you infer that this the space integral of rho is conserved. I'm doing the same thing. Okay. I don't know if that answers your question, but okay. Any further question?
No, sir.
All right. Just a couple of more things before I leave you. So remember the mid-semester exam is on 22nd from 10 a.m. to 12. Okay. So remember to appear for that. Many of your friends are not here. Please tell them to attend that exam and appear for that exam. And I have decided whatever I discuss in this last lecture, I will not give in the final exam and in the mid-semester exam. So this is just for your information, so that you are not overburdened with studies. So focus on your the usual classical mechanics part. And the last thing is that okay, remember to submit that homework, like this, reading that 1 or 2 papers and writing something. It's good for you. You will learn a new thing, hopefully a new perspective of diffraction and quantum mechanics if you do that. And I will give preferences to people who actually submit that thing when I need to choose someone for the seminar course. And third thing is that after the end of the semester, you would be asked from the institute to provide feedbacks. Okay, and I encourage each and every one of you actually fill that up. Okay, so even if you do not, even if you do not have anything good to say about this course, make sure you still fill that up. And if you do not like this, you say that there explicitly. And when you so if you have positive comments, perhaps you do not need to explain. But if you have negative comments, try to make sure that you explain, uh, mm, because there would be spaces for comments. Suppose you did not like that part of the class or that part of the course or this style, so explain now what happened in there, if it was too technical for you or something, whatever you felt like, right? And it's completely anonymous, so you don't have to worry. And even if you're even if you say it directly in front of me, I would not mind at all. So make sure you fill that up. It helps us to judge for ourselves how the courses are going, and maybe when we design the course for the next year, what kind of things need to be a bit more adjusted, so that it becomes more acceptable um, to the students. Okay, so make sure, so you are making the course better for the upcoming generation, so it is your contribution, so I encourage you to do that. All right then, so that's it. I have no further comments. Do you have any comments here? All right then, so I will see you during the mid semester, and well, after that Dr. Pakira will take over. So okay, good luck for the exam. Bye.